Hi everyone. Is this working? Is the mic on? Yep. Okay. So it's a really great pleasure to be here. Thank you very much, Professor Dylan, for inviting me here.
Harpreet.
And Harpreet, I mean, he's an old friend of mine actually, so there's some history. Harpreet was actually an intern when he was a graduate student working at Bell Labs. This is about 4 years ago. And so we've had a great history together, working together. He's actually a co-author, a collaborator on the work that I'd like to talk about today. And thank you all for coming today, Friday afternoon. Are they taking attendance? Is that why people are All right. So I'd like to talk about wide area communication challenges for the Internet of Things. And so what does this mean? So first of all, what is the Internet of Things? Internet of Things is sort of a very trendy term that a lot of people throw around now. And in addition to terms like cloud processing and big data, people like to talk about the Internet of Things. So for me, what this means is it's a general technology for connecting physical objects with the Internet. And so you can think of a physical object as being something like a health monitor, a power meter, a drone. You might have some device that's connected to a package or your pet that you want to track the location of. And so you want to have some way of connecting these physical objects with the Internet, the cloud on the right side. And you can do this through a wired connection, or you can do it wirelessly. And so here are some examples of wireless nodes, access nodes. You can have these devices connected through a base station, through a handset, through a Wi-Fi access point. So some applications, like you might have a health monitor on your body that's connected through Bluetooth to a handset, and the handset is connected through a cellular connection to the network. And so there are different options of connecting these devices wirelessly to the cloud. And then in the cloud, you have processing for billing, for device management, for running the actual applications. You might have some data analytics up in the cloud. And so together, this ecosystem is what makes up the Internet of Things. But today I want to focus on, say, one particular part of this, which I think is very interesting, which is the particular case where you want to have wide area coverage for connecting your devices to the cloud. And so this means that you want to rely on some wide area wireless infrastructure. For example, a cellular base station. And so this talk then is going to focus on applications where you require wide area coverage, where you're served by a cellular base station. And so this is going to be the infrastructure through which your device communicates with the network. And so for each of these sort of examples, you can think of how a cellular infrastructure could be used. So applications for, you could have remote health monitoring. If you didn't have a smartphone, if you didn't have a nearby access point, Wi-Fi access point, you're walking outside, how can you keep track of someone's health? For tracking objects, you might not be near any smartphones or access points. Similarly, for say drone control, you want to send a command to your drone. A cell phone tower might be the best way to access that. And then for remote reading of power meters, you want to do this in a wide access way in order to reduce the cost of deploying other infrastructure. So we want to focus on communication between these devices and the cellular base station. This is sometimes called machine-to-machine communications, or M2M. And so if we think about the challenges of communicating for these IoT devices versus conventional broadband communication for cellular networks, there are a couple of differences. If we talk about here in terms of sort of the range versus the required device energy, we can think of say, three classes of communication systems. One is short-range IoT, where you could use the IoT device to communicate with a smartphone or a Wi-Fi access point. So here the range is relatively short, and then the device energy required to do the transmission is relatively low. Over here you have cellular broadband. The range is further, data rate is higher, and it requires more energy. And then here you have, say, a new generation of cellular IoT technologies where you're evolving the LTE cellular standard to accommodate lower data rate communications. You have these dedicated systems based on these companies from Sigfox or Semtech for enabling IoT-specific communications on a wide area network. And so the goal for us, though, is to really try and reach this point here. We want to have a very long-range system and have it be very energy efficient from the device point of view, because in many of these applications, you might not be able to charge the battery on a nightly basis like you would in, say, a handset. So another way to look at this is in terms of these 4 dimensions. If you want to compare cellular broadband with cellular IoT communication, cellular broadband, you have both uplink and downlink traffic. It's typically streaming is the sort of most challenging type of communication. You might have a relatively few number of devices, maybe 100 per cell, but you can charge your battery once a day. For IoT, a lot of the applications require uplink transmission. So you have a sensor that's taking a measurement, and you want to send that data back to the network. So that's an uplink transmission. That data is going to be a relatively small payload, say on the order of a few hundred bits, a few thousand bits, and it's really a different type of information that you're sending compared to something like streaming video. So if you only had a few devices sending small payload, that's not a very challenging problem. But what makes it challenging then is that you have a very large number of devices, say in the order of 10,000 per cell, 100,000 per cell. So, the number of devices is large, but the payload per device might be small. The total, the product of the number of devices times the payload per device is still going to be a relatively large number that's comparable to what you would have gotten in the broadband setup. And then you have the final challenge here of the energy efficiency. So in a lot of these IoT applications, like I said, you might not be able to charge the battery daily. You might put a tag on a meter that you put out in the forest, and you would then just wait for the battery to die out, and hopefully it would last, say, a year or 2, and then you just replace the whole device. And so the IoT devices, a lot of these applications require very, very high energy efficiency. So the important metrics then, I think, are the number of devices, so you can think of that as a capacity metric, and the energy per device. So you want to increase the energy efficiency, you want to increase the number of devices that you can support. So we can think of 2 general problems in this area, each one of these problems addressing the 2 separate metrics of interest. Okay, so we can formulate a sort of general framework for these problems by saying you're given some resources in time and in frequency. You have some desired payload. Let's say that's 500 or 1,000 bits. That's some measurement that you want to take. Maybe it's the coordinates of the device that you want to send back to the network. And so first problem is a capacity problem. We want to, given the maximum transmit power of a device, how many devices can we actually support to communicate the desired payload size? So that's a capacity problem. The second problem is an energy problem. So now it's sort of the dual of this. So now given a certain number of devices, how can you design the transmission and the protocol in order to minimize the energy required for each device to send its desired payload of bits? Okay, so I'm gonna talk a little bit about both of these problems, give you sort of an overview of the solutions that we've come up with. Just there'll be some math. It'll be pretty high level, so hopefully it'll be understandable. So let's talk about problem 1 first. It's the capacity maximization problem. So again, we're given a set of resources in time and frequency. Let's say it's 1 second in time, and then say 1 megahertz of bandwidth. And so the 1 second time resource, you can think of that as your latency requirement. Right? So you can think of, say, a bunch of devices coming, wanting to transmit their data on the uplink. They have some, let's see, so they have some payload that they want to send. They arrive at the beginning of this 1 second frame, and there's 1 megahertz of bandwidth. We want to serve as many of these devices as possible within this 1 second, and that's the latency requirement, which is reasonable for a lot of, say, metering applications where you don't have to have, say, millisecond level latency. You can wait a second to get the power reading of your meter, or even you can wait 1 second to get the location of your pet. Right? So it's not that time critical, but there are some applications like controlling drone critical. But let's focus on these latency tolerant applications. Okay, and then you're given some maximum transit power per device, given milliwatts, and then the problem is to maximize the capacity in terms of the number of devices that you can serve. Okay, and then so one dimension that we're going to explore here is what's called coordinated versus uncoordinated access. So what this means is that if you think of a conventional cellular system based on the LTE standard, this is a coordinated access scheme, which means that you have a bunch of devices, they want to send something up on the uplink. It's coordinated in the sense that the base station tells each device on which resources to do the communication on. And so you can see then it's done, in this case, where each of the different colors represent different devices. They're allocated on separate orthogonal resources. There are no collisions, and then you can schedule it to optimize some performance metric that you have. And so you have a lot of control over the transmission, but the price you pay is the overhead in sending this information to the device. So the base station has to tell the device, please transmit on this frequency band and during this time. So there's some overhead incurred in sending that downlink control information. In contrast to that, in an uncoordinated access, if a device thinks that if it has data to send, then it just sends it. It doesn't wait for some information from the network to tell it how and where to send. The device has some notion of, it has some protocol, it has some rules programmed into it so that when it has something to send, it'll follow those rules and send it. You might have some collisions. So in this case, the yellow user collided with the blue user because they transmitted on the same time frequency resources. And so you have some collision. The throughput might not be as high as in the coordinated case because of these collisions. But on the other hand, you've saved in terms of not having to, you've saved in terms of overhead because you don't have this control information. Okay, so going a little bit deeper into this, if you think of in coordinated, then you can think of, let's say you have a device and you have a base station. This is just sort of a timeline of how coordinated access occurs. You have a device, it sends its ID to the base station and says, I have some data I want to send. And then the base will respond and say, okay, please transmit on this resource. And the device transmits the data on that resource, and the base sends the acknowledgement. Okay, so like we said, there's more overhead, there's no collisions, and it's good for larger payload sizes because what this means is that you're investing overhead, and it makes sense to invest this overhead if your transmission is a very large payload, because then you've guaranteed through the scheduled coordinated transmission that this transmission of the very large payload will have some guaranteed delivery and therefore it was worth investing some small amount of overhead. But if you're sending a very small payload, it might not make sense to invest in that overhead. Okay, and so that's what happens here. The coordinated access, the device wants to send data, it just sends its ID and the data payload in a random access channel, and then the base just sends an acknowledgement. And so there's less overhead, it's positive emissions, but it's good for smaller payloads because you don't have that overhead. So the question is, if we look at okay, so there's been a lot of work in the coordinated access schemes because that's what's done in conventional LTE networks. In uncoordinated access, there has also been a lot of work done here, except when we started looking at this, as far as we could tell, there was nothing that really described the optimal way of transmitting on the random access channel. And I'll explain in what sense we attempt to achieve optimality. But this was sort of the goal that we had for us. This is maybe a few years ago. So the problem then, if we look at the system model, we have some resources, some slot duration of, say, t seconds. Let's say that's 1 second. We have bandwidth, say it's 1 megahertz of bandwidth. And then we have some downlink beacon transmitted by the base station to provide some notion of timing to the device. So this the device knows, okay, here's the beginning of a 1 second slot. And then during the slot, there are k devices that want to communicate. K is a realization of a Poisson random variable. And so what this means is that there's some average arrival rate per slot. On average, it's, say, lambda, say if t is 1 second, lambda is an average number of devices per second that would want to have service. So let's say lambda is 1,000. And so if that's the average, then the actual number could be, say, 900 to 1,100, something like that. So there's some realization of this Poisson random variable at the beginning of the slot. K devices want to transmit, and they want to transmit a payload of L bits. Let's say that's 1,000. And these devices are uniformly distributed in a cell. So imagine you have a circular cell that's 1 kilometer in radius. You have a base station at the center of the cell. You have devices that are uniformly distributed, and there are K of these devices, each wanting to transmit 1,000 bits. Okay, so now given 1 second, 1 megahertz, 1,000 bits, and some target outage probability of delta. So this means that we allow some small fraction of devices to not actually be served. And let's say that's something like 1% or 5%. And we want to maximize this arrival rate, lambda. So remember, that's the average number of devices per second that one service. So we want to maximize this such that a device transmits its L-bit payload with probability of 1 minus delta. So delta is the outage probability, it's 5%, and we want it to be successful with 95% of the time. Okay, so the overall problem then, given these parameters, let's design a protocol to maximize lambda, the number of devices that we can support per second. Okay, we can think of, let's talk about a, say, conventional technique that we can use as a baseline for comparison. We want to derive the optimal technique. Let's talk about a baseline just to sort of get familiar with what the possibilities are. So here we have our resources, and we have, say, 1 megahertz of bandwidth. We're going to look at a conventional technique known as slotted aloha with frequency division multiple access. And so what this means is that we have our spectrum, we divide it, we partition it into capital B bits of bandwidth W by B hertz. B is a parameter that we'll design for each device with some known channel. So this is the realization of the wireless channel between the device and the base station is G of K. And that device will select one of those capital B bins to transmit on. And there will be, that transmission will be successful if two things happen. If first, that's the only device transmitting on that bin. If another device transmitted on the bin, there would be a collision. you could resolve it if you had some sophisticated receiver, but let's assume that if there are collisions, then that transmission is not successful. And then the other requirement for success is that the link budget is met. In other words, the channel is such that when the device transmits with full power, then the signal-to-noise ratio of the receiver is sufficient to support the data rate for communicating data, L bits of data over the W over B hertz of bandwidth over this time t. Okay. And so this is the average number of devices per slot. Communicating L bits can be written as this expression here. I mean, it's basically saying there are B bins. Here's the probability of a device, of only one device choosing a bin. Here's the probability that the link budget is met for transmitted L bits. And then you want to maximize this with respect to B. And so B is the number of bins you can design your system to have the optimum number of bins. Okay. So from this we have some expression for the number of devices that can be supported by this baseline slotted OFDM, slotted FDMA, slotted low-power FDMA. So let's talk now about what the optimal strategy is. So the optimal strategy is based on information theory techniques on the multiple access channel. And so for those of you familiar with that, the multiple access channel is when you have a bunch of devices and they're communicating to a common receiver. And in the conventional multi-access case, it's scheduled in the sense that the base station knows which devices are communicating. It knows to look out for each of these devices and to demodulate them using some knowledge about their code books. The optimal strategy in the multiple access channel is to have each of the devices transmit over all of the time frequency resources. And they're all overlapping in time and in frequency, and you have to use some sophisticated successive interference canceller to jointly demodulate all of these devices. So that's say, the conventional optimal strategy for a multiple access channel. Here, we want to, it's different because the base station, the receiver, doesn't know in advance which devices are actually going to be transmitted. Because you remember, this is a random access channel. A device wants to transmit, it just starts transmitting. So the base doesn't know ahead of time what devices will be transmitting. So the overall strategy then is as follows. So the transmitter, let's say there are k devices, and the first thing it does, it flips a coin, and with probability theta, it decides to actually transmit. So there's a possibility, so theta is a parameter that we're going to optimize over, and so there's actually a chance that even if that device wants to transmit, it's not going to transmit. And that might, that's a parameter we can optimize over. And we want to take advantage of that parameter because remember, we have some outage probability delta that we can, we don't have to serve all the devices necessarily. Okay, and then each device encodes its data with one of Q randomly chosen code books. And this is sort of an information theoretic design. It transmits over all the resources, so over the entire W hertz bandwidth in T seconds, and it has some short preamble that identifies which code book that it's using. So again, this is sort of a detail of the information theory proof that's required to show that this is optimal. At the receiver, then, you're listening for this preamble, and once you detect that, then you know which devices are, which code books are active, and then you jointly decode the largest set of users whose rate vector is in the corresponding capacity region, treating others as interference. Okay, so this is a way to explain this without getting into sort of the information theory details is, in essence, you have, let's say you have 7 users that want to transmit. Each one flips a coin, and then 3 of them actually decide, okay, they're not going to transmit. Out of those remaining 4, they're all going to transmit, except the base station, because of the link of this one is too far away, so it won't be able to to be decoded reliably. So the base station doesn't even try to detect that one, but it detects these other three in the presence of interference of this one. Okay, so this is the basic idea of the strategy. We have some expression for computing the average number of devices that are successful. We can skip over this. We can skip over some preliminary numerical results. Let's go to a, let's put this back in the framework of what we talked about at the beginning, where we have this coordinated and uncoordinated, framework. And let's look at the performance of our uncoordinated optimal strategy that we just derived. Compare that with the slotted aloha strategy that I described. And let's compare that with a sort of conventional LTE system which has slotted aloha in the first random access channel case, followed by a response from base, followed by some scheduled transmission. Okay, so there are three options that we want to compare. There are some parameters that characterize the system. And so just to give you a feel for how our proposal performs, this is the metric of interest. This is the number of devices, the average number of devices per second that it can be supported by our system. So the higher we are, the better. The x-axis is the payload size. And so we have the three curves. The blue curve here is the coordinated transmission, the two-stage transmission. This is, say, conventional LTE. The dotted red line here is the baseline for the uncoordinated transmission based on slotted aloha. And you see here that there's a crossover at around 50 bits. So what this means is that if the payload is 50 bits or less, then it makes sense, then slotted aloha performs better. So for very small payloads, don't invest in the overhead, just use slotted aloha, transmit if there are collisions, then transmit again. And, but then if the payload is larger than that, then it makes sense to invest in the overhead, do coordinated transmission. But then on top of both of these is uncoordinated optimal. So the uncoordinated optimal actually does better than the coordinated. But the trade-off there, though, is that the complexity is very high. So I described to you the strategy for the optimal transmitter and receiver, but it's actually very difficult, if not impossible, to do this in practice. So, so you actually have to sort of back off from this optimal strategy, move more towards the baseline slotted aloha in your more practical implementation, and so that's something for one of you guys to maybe think about. How can you have a practical implementation of a random access technique that does nearly as well as the optimal, but whose complexity is significantly less? Okay. All right. So that's problem one about capacity maximization. Let's talk about problem two now. This is for energy minimization. So getting back to the original framework, remember we have some resources, we have some payload, we have some devices with known channels. And now we want to, the goal here is a resource allocation problem. And so now we're thinking in a scheduled, coordinated mindset. So we're not in the uncoordinated random access mindset. Think about a scheduled system. We want to allocate resources to these K users in a way such that we minimize the total energy expended by these devices. Okay, and so for example, here are the resources. And let's break them up into small chunks, each of bandwidth delta F and time delta T. And let's say there are 12 of these chunks, and we have 4 users, and we want to assign the resources to these users, and then tell the users how much power to transmit on each of these resources and you want to do that in a way which minimizes some overall energy metric. Okay. And so the first metric we want to talk about is the total energy expended by all of these devices, so these 4 devices in this case. And so this sum energy metric is meaningful if you have multiple devices. Let's say they're moving throughout your cell, and if you minimize the total energy, then in some sense you're minimizing, you're doing something that's uniformly good for these users as they move around the network. So that's a meaningful metric for these mobile devices. And we want to allocate resources in an orthogonal way. So for a given resource, we restrict ourselves to having at most 1 device per resource. And you could look at something more sophisticated where you have users sharing resources, but that's an extension that someone else can do. Okay, so the optimization problem is let's look at a particular resource that's allocated for a particular user. So one of these little squares, resource n, that's allocated for user device k. And let's say that we allocate E kn t joules. Okay, so k is the device index, n is the resource index, t means the transmit energy. And the reason why I have a superscript t is because I want to then introduce another energy, which is the overhead circuit energy. Okay, so think of t, E of t, as the energy that's the power amplifier of that device. And so this is the energy to enable the device to transmit with some power ET, and with that energy, and for some given channel, I can communicate log 2 of 1 plus SNR bits per second per hertz, and then we multiply by the bandwidth and time resources for that little block, and this is the number of bits that we can communicate for that box. Okay, and then so the total energy expended by that device transmitting on that resource is E of t, which we just, so this at this point this is something that we've assigned, and then there's some overhead energy, which is E of c times I of ET. And so this I is just an indicator function, which is 1 if ET is greater than 0, and it's 0 if that resource is not used. So in other words, if a resource is used, it costs EC joules to use that. If it's not used, then you don't have to account for that. So this is just some overhead energy that that is some sort of practical modeling of some overhead energy in the transmission. So in practice, you can think of this as something like the circuit energy that would go into the baseband processing in order to communicate this data. And so so of, in some sense, independent of what the transmit energy is, then you're going to expend some overhead energy for the circuit. Okay. And there might be some dependence on the actual data rate, but let's say that it's independent for now, just to simplify things. Okay, so then the optimization problem is we want to minimize the total energy of all devices. So this is the energy for one device. We sum for one device, one resource. We sum over all the resources. We sum over all the devices. We want to minimize this total energy, and the knobs that we have to turn are the actual assignment of energies to each of the resources and the allocation to each of the users. So we're minimizing with respect to E, K, and T, subject to, we want each device to communicate L bits, and we want at most one device assigned to each resource. Okay, so I think it's clear what the optimization problem is from sort of the written sentences over here, and then this is just the math to describe that. Okay, so if we think about the simple case of allocating resources to one device. So let's say you have n resources, you have a channel that's flat, meaning for all the resources, the channel realization is the same, independent of the resource. We have some payload L bits, and you want to allocate some optimal number of resources, nu star, which is less or equal to the total number of resources, We want to minimize the energy of that device. And okay, we note that for any allocation of NU resources, so let's say I allocate 5 resources to this device to communicate L bits, how do I determine how much energy I put into each of these 5 resources? Well, because of the concavity of the log function, log2 of 1 plus SNR, it turns out the best thing to do in terms of energy minimization is to put equal power into each of these bins, equal energy into each of these bins, and that actually minimizes the overall energy for communicating your desired payload. So for any number of resources that you allocate, split the energy equally among those resources to communicate your L bits. Therefore, if you allocate NU resources, then you transmit with energy ET such that you have N resources times log2 of 1 plus MUE, which is the basically the number of bits per resource. And then you have N resources, and you want that to be equal to L. So you can solve for given L and for given NU, you can solve for E. Okay, and that's what's done here. When we calculate the total energy for this device is the number of resources times the energy per resource, which we've solved from up here, plus the overhead circuit energy. And so for each resource, you expend EC joules. Okay, so just remember, here is some formula for the energy for a particular device if we allocate NU resources to communicate L bits. That's the expression for the energy, the total energy expended. Okay, so now let's look at this expression of the total energy as a function of NU. And so then the problem is basically finding NU which minimizes this total energy. So in a special case, and remember this is just a single device, in a special case where there's no circuit energy overhead, EC is 0, then it turns out that the total energy decreases monotonically as you increase the number of resources. And you can see that here. If EC is 0, then as you increase N, there's some linear increase in N, but there's some exponential decrease in the energy per resource. And so overall, the energy decreases as you increase the number of resources. Therefore, if you have a total of N resources, then you have just one user. To minimize energy, you want to give as many resources as possible to that device, and that number is capital N. You guys got that? Okay. Okay. So in other words, if it's 0 circuit energy, you want to transmit with all the resources, with your N total resources. Now, if you have non-zero circuit energy, then this function actually is no longer monotonically decreasing, and in fact depends on EC. So there's some optimal value of N, number of resources, to minimize this total energy. And this makes sense, right? So imagine that the overhead circuit energy, if that's extremely high, then every time you use a resource, you're going to incur this cost. Therefore, it might make sense to just transmit with one resource, because if you actually transmit with 2 resources, that overhead cost would increase the total energy, and so depending on what this EC is relative to the ET and the payload, then there's some, in general, some optimal value, let's call it N star U, for minimizing the energy for that device. Okay, so the optimal allocation for multiple devices, we can think of solving this using a greedy algorithm. Okay, so now let's consider the case. Let's say there are 2 devices. We have an orange device, which is farther away from the base than the green device, and so each of these wants to communicate some payload, L bits, and so the greedy algorithm. So the goal then is, how do you determine how many resources for each device to communicate the L bits in order to minimize the energy? And so the algorithm does this. It says, initialize for each user, find what this N star is. That's the starting point for each user. The N star can be computed from the previous single user analysis. And given from that starting point, so you're starting here, user 2, starting here for user 1, so 5 5 resources for user 2, 4 resources for user 1. It's a greedy algorithm, which means, and so you have a total of 9 resources allocated. Let's say the total number of resources you have is 5, and so you basically want to step back from 9 resources, take 1 resource away per step until you have a total of 5 left, and that because that's the total number that you have to actually allocate. How do you decide which resources to take away from which user? You do it in a greedy fashion, which means that for the first resource, you want to look at taking away the resource which results in the least increase in the change in energy, right? Because here you want to minimize the total energy. So for each step, you want to take away the resource. And when you take away a resource, then that device will require an increase in the transient energy. But you want to remove it from the one that results in the least decrease and least increase. And we're going to cursor down. And so for the first step, I want to remove 1 resource from 2. So now it requires this amount of total energy. On the second step, I want to see removing 1 resource from this other user results in the least increase in total energy, and so on. And so this is the greedy algorithm, which is conceptually pretty simple, and the implementation complexity is simple because it's linear in the number of resources. And it turns out, though, that the greedy algorithm actually achieves the optimal resource allocation for minimizing the sum energy. So we had that somewhat daunting optimization problem a few slides ago, and we can show rigorously that we can, in fact, achieve that optimal resource allocation using a relatively simple greedy algorithm. We can do a similar greedy algorithm for a different metric, which is the minimizing the maximum energy of the devices. I'm going to skip over that in the interest of time. And here are just some numerical results showing, say, you have a network of 100 devices distributed in a cell. Each one wants to communicate 500 bits. If we have some baseline algorithm, which is some, say, naive algorithm, which does equal resource allocation to the 100 devices. So let's say you have 1,000 resources, allocate 10 resources for each of the users, and then figure out the energy required to communicate with 500 bits using 10 resources. So that's the green curve here. And then with the min-sum algorithm, which we talked about, that's the blue curve. We can reduce. This is the maximum device energy, which can be right. So this axis is actually for the second metric of the maximum device energy. This figure over here is for the sum device energy. And so we basically get an improvement of about 25% using this simple greedy algorithm for allocating the resources to the devices. Okay, so this is the end of the talk. So I've talked about uplink communication for the Internet of Things in a cellular network. Each device wants to send a small packet of information. We talked about these 2 problems, one for maximizing capacity, one for minimizing energy. And I've made a lot of ideal assumptions here, and I think there's a lot of extensions for this to make these techniques more practical, considering things like channel estimation, better device energy modeling, some cross-layer design, non-ideal cancellation, and so there are a lot of opportunities for other people to contribute to these problems. And I want to thank you very much for listening on this late Friday afternoon, and I'd be happy to answer any questions.
I'm not sure if this is included in like a cross-layer design or if it's not in the scope of the M2M model, but so like with you talk about the low power and you mentioned like the tags being out in the woods. It seems to me that if you are having that kind of isolated situation, and especially with cell phones and being in the woods, generally you don't have a very strong connection even with like a cell phone where the battery only lasts for a day. So like do you guys do work on kind of like a cellular almost like not ad hoc, but like extensions?
Right, so we call that the range extension problem. And so, so in a conventional cellular network, you might design it to have some maximum range of the cell size. It might be 2 kilometers. But in an IoT application, you might want to have the device at 2 kilometers, but in the basement of the building. So you need to extend the link by, say, 20 dB, and that is another dimension that people talk about when designing IoT communications is this range extension problem. So yes.
We talked about two kinds of things, like coordinated and uncoordinated. So why don't we go for something in between, like that device in the same frequency band, they can sense the channel, and whenever the channel is free, then it can transmit, rather than transmitting it continuously. So we can wait for some fixed amount of time. It can check whether the channel is free. It can transmit as it can go to the power save mode, and it can after some point of time again it sense the channel. And each device will get scale allocation of channels to transmit.
Yeah,
so why don't we use this?
Yeah, so you're suggesting some sort of hybrid mode where the device can sense the channel and then decide which mode, coordinated or uncoordinated. And so we have looked at those sorts of generalizations, and that seems like it seems like in certain situations you could do better.
There are some power constraints because if the range is high, every device needs to sense the channel. In that case, it might be difficult because if you want, because some 5-6 devices are in the same frequency band, they might be far away. Because if you need to sense the channel, it needs to sense energy from the other signal also, the other device also.
Right. So,
but as we are limiting it to picocells in the Internet of Things application, I think this should be
so the question is, how well can you sort of sense the presence of the other devices?
Yeah.
Right. Yep, very good.
Thanks for coming. But my question was, have you thought about having kind of tiered structures? So some structures that get part of data and then decide to transmit once it's like pretty.
Oh, are you talking about maybe a relay?
Something like that.
Right. So, so you're saying that if you have a cell, you have a base station, but you might have some relay here where a device near the relay will transmit to that, and then the relay transmits to the base station. So that's another generalization, and people have looked at these relay networks. And there are definitely situations where that makes sense. I personally haven't looked at that. But that's definitely a valid sort of extension.
I have one concern in the uncoordinated approach to increase the number of devices about the effectiveness of having like 5% of devices that are not served. So are these like randomly changing from one time frame to the other, or there is like one device that keeps on?
Yeah, so typically those would be the devices in outage, the ones that don't get served, are going to be the ones with the 4 channels that are at the cell edge. And that's just sort of the reality of wireless communication networks. So even in conventional cellular networks, there's typically some outage, and those are going to be applied to the users with the worst channels. And that's just something that you have to accept. because otherwise, if your outage is 0, then you have to use way too many resources to achieve that, and that's not. So you're basically penalizing a few users for the good of the whole system. And if you have some fading, then even if you're at the edge of the cell, maybe you might have a good fade, and you might actually get served once in a while. But in the end, you want to engineer your system to have some low outage probability, and you just have to do something.
Like to minimize the number of sequences, the fault, number of times that the same device has been unable to send.
That's right. You can engineer it to sort of account for that cell edge performance.
So in your formulation of the optimization problem, so we were optimizing the number of bins, right? So
In the FDMA case.
yeah, but shouldn't there be a constraint on the total bandwidth by the number of bins, because each device might need a minimum bandwidth to transmit. So shouldn't there be a constraint on that?
Our assumption is that for a given number of bins, you have a given bandwidth for that subband, and then if the device wants to communicate over that W over B hertz, it needs to transmit with a certain amount of power to transmit those bits over that frequency resource. And so this is a somewhat simplifying assumption. I think maybe what you're suggesting is that you could optimize over the partitioning of the bandwidth. So that's another degree of freedom that you could account for it, right? And so that could be some further optimization that you could do. Right, and it's not clear to me how much better that would be than this, but possibly it's something to consider.
So my understanding of how you mentioned that you have the difference between coordinated and uncoordinated access, and the majority of models, my understanding, seems to use coordinated access.
Well, so I guess my statement was that existing LTE systems use the coordinated scheme.
So then the LTE hardware that is out there right now and that currently my phone can connect to, is that something that you could easily, by using, is it a software change to implement an uncoordinated access strategy, or is that something that if, say, Verizon wants to start offering a separate network for LTE network for all of its devices, they have to go out and put new hardware out?
They have to put new hardware, and it's more than that. There would be required. These LTE cellular networks are based on standards that are decided by dozens of companies. And so you would need to actually change the underlying standard, have hardware and software built to that standard before it can be deployed as a system. So these strategies, most likely, if they do get implemented, would require the next generation 5G standards. And so that's what we're thinking about, of suggesting some of these changes in the 5G standards.